All right, we spent a lot of time talking about feedback, right? We saw different ways of looking at it. We saw that they had the asymptotic gain formula, and we also saw that we had the loop gain, which was an invariant of the loop, and we defined both unilateral and bilateral loop gain. Now, the interesting thing is that, so why do we need to worry about these many things, is that feedback had these really beautiful properties, right? I mean, it allowed you to desensitize the circuit to the forward gain. It allowed you to broaden bandwidth by trading the gain with bandwidth and all sorts of these other properties. So what were the problems? The problems really arose from this plot that we started off with several lectures back, right? You remember we said if you have an amplifier with some dynamics and then you apply some sort of feedback to it, what happens is that we saw that when you have the A times F was much larger than 1, then you basically got a transfer function that looked like F. And when it was much smaller than 1, you basically followed the transfer function of A, right? A of j omega, and this was basically 1 over F of j omega. But in between, interesting things can happen. And now we are going to talk essentially about why and what can happen in here. So in other words, when the loop gain was very large, you basically were the forward transfer function was determined by the feedback, right? It was 1 over F. Another way to see the simplified way of seeing it is 1 over 1 plus AF, right? H. If you think about A being very large, then for A, or more accurately for AF much greater than 1, this is going to be 1 over F, which is H infinity. And for AF much smaller than 1, this is basically going to be just going to be A. So that's this second part is here, this first part is here. Now, when you're comparable, interesting things can happen. So you're trying to think about those in several different ways. So the first thing we are going to do, we're going to go through an example, and a circuit example to develop some intuition about some of the things that can happen, and some of the, and also it is to dispel some of the misconceived notions that you can see in many places, including textbooks. So it's an interesting circuit in that sense. So you have an I in, let's say you have a current, right? That's going through, and we are making a 3-stage amplifier. This is a very simple amplifier. We are not going into the biasing details and things of that sort. So you have 3 stages of amplification with the same load, right? So you have 1, 2, and 3, right? And we call these resistors R1, R2, R3. And then there's source resistance RS. This can be a model, for example, for a photodiode or something like that, photodetector in an electro-optical. So this can be a transimpedance amplifier, for example. And then you go to a buffer stage, a follower stage, which is biased with a current source. So make it very simple and drives the output, V out. Right? So there are 3 transistors, M1, M2, M3. And then let's say there are 3 capacitors here. So this capacitor basically at the input, C in, which has 2 parts. It's the capacitor of the transistor, let's say CGS, plus the capacitors of the diode, CD. So this can be part of the capacitors coming from here, part of it is coming from CGS. Then you can have a capacitor C1 and a capacitor C2 for the gate capacitors, or the gate source capacitors. So this is R1, R2, R3, M1, M2, M3, M4. So this doesn't look like something fancy, right? I mean, it doesn't look that unusual. We have even ignored C mu's to make our lives easier. Just assume that these are the dominant capacitors. It's a 3-stage amplifier. So what is its trans resistance? If you look at the low frequency trans resistance, what is it? Basically the ratio of V out to R in. So Z of 0, trans resistance, is defined as V out over I in. So what is it? This current at low frequencies goes through RS. It produces a voltage, right? So it's the voltage is RS. Then it goes through the gain of this first stage, this voltage from here to there, which is what? GM1 R1. So you get GM1 R1 with a minus sign. And then you go through another GM. So now you have the GM2 R2 Fine. Basic calculation. Another GM3R3. So you have a minus. Each one of them is an inverting state. So you have a minus here, minus here, minus here. 3 minuses still gives you a minus sign. And then you have a follower. What's the gain of this follower from this input to this output? 1, right, because it's a current source, ideal current source. So it's a voltage divider, resistive divider between infinity and Rm. So it's 1. So this is your low frequency transfer function. So that's Z naught. And you can evaluate it or estimate it or calculate. Now, what is Z as a function of frequency? That is also very straightforward for us to calculate by now. The tools that we have at our disposal, this is really trivial, right? How many poles? 3. You have 3 capacitors. They're not forming a capacitive loop. They're independent. They're not in parallel with a voltage source or something like that. How many zeros? None. Because if you short circuit any one of them, infinite value, any one of them, you're not getting anything through. So there's no combination of them that you can actually come up with that would give you anything. So there's no zeros. So we know that the transfer function looks like Z of 0 over 3 time constants, 1 plus tau in S. OK, so now we don't know this yet. We haven't discussed this yet. But we know one more thing. These time constants are also uncoupled, right? Because what the resistance each one of these capacitors sees is independent of whether or not the other capacitors are shorted or opened, right? Shorting or opening of the other capacitors would not change the resistance seen by each one of them. So there are 3 uncoupled time constants. There are 3 real poles. So you can write it as 1 plus T in S, tau n is, plus 1 plus tau 1 S, times tau 1 plus tau 2s. OK, fine. So, and what are tau 1 and tau 2 and tau 3? You can write them. Tau n is what? What is tau n? They're trivial, right? The resistance seen by this guy. Rs. So it's Rs Cn. Tau 1, again, the resistance seen by this guy. R1 C1, and tau 2 is R2 C2. OK. So from a frequency analysis, high frequency analysis, this looks pretty straightforward. I mean, this is as simple as it gets. OK, and we can do a numerical example. So let's do it. We are going to be doing numerical. This is numerically, so we're going to look at simulations and see what happens. So for the numerical example, so these are the parameters we are using. So the parameters for our numerical value is GM. We are assuming all 3 GMs to be 2 millisiemens. We are assuming CGS of 500 femtofarads. So these are like pretty low frequency transistors. We are assuming R1 equals R2 equals R3 equal 5 kilo ohms. RS of 1 kilo ohm. And CD, the diode capacitance of 1 picofarads. So these combined give you a total capacitance of Cin. So Cin would be 1.5 picofarads, and these guys would be simply 0.5 picofarads. And with these, you can calculate the time constant. So the time constant tau in is going to be 1.5 nanoseconds, right? And R1C1 is 5K times that is 2.5 nanoseconds and 2.5 nanoseconds. So you have 3 time constants. 2 of them are equal to 2 overlapping poles. So you have 3 left half plane poles. This corresponds to a pole of P1 or Pin equals negative 2 pi times 106 megahertz, 106 megahertz. This is P2 equals P3, or P1 equals P2, I guess. We call that Pn. It's going to be negative 2 pi times, what did we say? 64 megahertz. OK, so there are 3 poles. Now, if you look at the plot, so that the top 2 plots are this is the Bode plot. The amplitude and phase of the response of this amplifier, the way we've drawn it. This is an open loop amplifier. So this is what we see. You see that it has about, what's the total gain if you plug all these numbers in? So this quantity becomes 1 mega ohm, the low frequency trans resistance. It's 1 mega ohm, which is about 120 dB ohms. right? Fine. And then you will see that the Bode plot actually shows the same thing, right? You see that the Bode plot, the amplitude is at 120 low frequency, and then you can see the slope kind of starts dipping first and then dips more. You see that you have basically 3 poles, 3 left half planes forward. Nothing really exciting about this thing, right? I mean, it's very kind of vanilla. And you see, and the third plot, the lowest plot, is essentially the step response. So you see the step response of this thing, yeah, it just goes up and then it's kind of flattens, right? As it should. So it's very well behaved. Nothing fancy happens here. Nothing exciting is happening yet. So we're going to do one thing. We're going to add one resistor here. We're going to take a resistor from here and feed back some feedback resistor RF from the output to the input. RF. And what we are going to do is going to change the value of this RF. Essentially, we are going to increase the value of feedback, which means that we are going to reduce the value of RF. We will start from an RF of infinity and start lowering RF. The lower we make the RF, the more feedback we have, right? That's by definition, right? Because RF infinity is no feedback. So we get more of the output and feed it back to the input. If you want to talk about the type of feedback, you can see that these are kind of like adding current in parallel, so it's shunt. And here, basically, you're sampling the output in parallel. Also, it's a shunt. You're sampling voltage here and returning current here, if you will, if you want to think about it that way. OK, so RF infinity is something, right? I mean, you get something. Now, let's start with, so then let's go to an RF affiner. So the first RF value we'll pick is 500 kilo ohms. So now it's a pretty large, still pretty large resistance, which means that it's not a lot of feedback. And let's see what we get. So on this figure, what you have, you can see that this is now the new response of the system. So the DC gain, the trans resistance of this has reduced from 120 dB ohms to 110 dB ohms. The feedback has reduced as we expected, right? We also see some other interesting things. If you look at the amplitude plot, what do you see? You see some peaking, right? How much peaking do you see? It's about 4 dB of peaking. And look at the step response. What do you see? You see ringing, right? So we see ringing in the step response, and clearly something is happening. If you look at this kind of like this symbolic or kind of a cartoon plot that we had here, right? It is kind of some interesting things happening around here. And it exhibits itself both in frequency domain and time domain. So, there's about 4 dB of peak. Now, if we go from RF of 500 kilo ohms now to an RF of 150 kilo ohms. So now we are lowering RF, basically meaning that increasing the amount of feedback that we have. So now let's see what we get. You will see that there is, now in this plot, you can see that the peaking is a lot more. Your gain has dropped, your low frequency gain has dropped to 102 dB ohms, right? But you're peaking about 19 dBs. That's quite a bit of peaking, right? If it were 20 dBs, that means that it's a Q of 10 in your circuit, roughly, approximately. And you can see the time domain response. The time domain response of this thing now is like ringing a lot. You hit it with the step, it goes, right? And now, if you kind of like, now let's go a little bit further. So now we are going to go to reduce this resistance now a little bit more. So now we are going to go to a feedback resistance of 116 kilo ohms. Kind of starting to sound like arbitrary, right? Because I'm trying to get close to the interesting spot slowly. You have about 53 dB of peaking. That's a lot of peaking. And look at the step response. It's just ringing, very, very slowly decaying, right? And of course, your low frequency, you're applying more feedback, so you've reduced the gain at low frequency because you're basically A over 1 plus AF. The AF has increased, so you're just basically dropping that. And so there's a lot of peaking at 133 megahertz, 133 megahertz. So now we have reduced your feedback resistance to 112 kilo ohms. Now, this is interesting. First, let's start looking at the amplitude response, the step response. The step response now, instead of being a decaying sinusoid, it's a growing sinusoid, right? So it's now growing, and it's clearly unstable because for a bounded input, you have an unbounded output. One point to take away is that look at the amplitude response. It appears, and it is correct that that's what the amplitude response looks like. The peaking has actually reduced. Now the peaking is about 33 dBs. So if you look at just the frequency response, the Bode plot, linear Bode plot, and you were using that as a metric of your stability, it may appear that your system is more stable. So the lesson one is that you can't rely purely on the closed loop transfer function of the system and how much it peaks to say if something is stable or not. Actually, this one looks more stable than the one before, right? Just if you look at the frequency response. But it's not. Because what you're looking at the magnitude of something that has a right half-plane pole. And right half-plane poles and left half-plane pole in the magnitude plot look very the same. And in phase plot, they just produce an increasing phase as opposed to decreasing phase. But even that's not, that's a telltale sign, but again, it's not as obvious. So we need to have some method to look at these things more systematically. Okay, so let's continue. Let's go a little bit farther. So now let's look at and there's a special case. If you, for example, pick 115, you can pick a value of, if you make your RF, now you can tweak your RF, right? If you're playing something with this, you can tweak it and make it 115.4. So if RF was 115, RF of 115.4, there would be more and more significant digits if you want to get it exactly right, but you can get it close enough to see the behavior. So that's figure 6.9. If you look at figure 6.9, what you see is that at that point, if you break the loop, right, and if you look at apply a Vx, if you break the loop at some point, let's say at the output or at the input, then it doesn't matter. Actually, you can pick some, so you can actually break it here. Probably the easiest place to break it is here, right? If you look at this plot, because the way considering the capacitors we've considered, there are other capacitors, you can actually apply a Vx here, and your Vx, the forward loop voltage loop gain, would be your entire loop gain, right? Because your current loop gain here is what? Because you put a current source into this impedance from a low frequency perspective, it becomes infinity. So since your current loop gain is going to be infinity, it only is the voltage loop gain that would matter. And you don't have reverse loop gain here because you don't have any pathway for the signal to flow in the reverse direction, so that is your loop gain. So your voltage forward loop gain in this case becomes exactly your total loop gain, as we discussed before. And so, okay, so if you look at that and apply a Vx and look at Vy, what comes back? So, and look at it in simulations, you see that after the initial transient, as the capacitors need to charge, etc., they're identical. So around that voltage where you get basically something that doesn't neither grow or neither decays, if you look at your loop gain, well, your loop gain is negative of this quantity, right? By definition, is negative Vy over Vx. So your loop gain, by the way we defined it, or everyone else defines it, is -1. Which means that the signal that goes in comes back. This is a linear analysis right now, right? So if you put a sinusoid in, the same sinusoid comes back. And it would produce, so it basically means that 1 plus t, this t has become -1, which means that this is kind of like becoming a pole at that point. So that part is not that counterintuitive, right? So far that sounds reasonable. But now, so let's look at something. And if you look at this, so if you continue looking at this, what you will see is that we can actually calculate this loop gain, right? We can evaluate what this loop gain looks like. What is this loop gain if we break it here? We can calculate this loop gain. If we break it here, what is the loop gain? So the gain from here to there is what? Well, is it still 1? Because now you have this RS and RF, right? So what we really care about is the voltage gain from here to here, right? That voltage gain is the resistive divider between RS and RS. So it's RS divided by RS plus RF plus RM4, right? That's the gain of that follower stage. So there's an RS divided by RS plus R4 plus RM, oh no, not R4, RF plus RM4. So that's a divider ratio here. And after that, you have the gain of the 3 stages. So the low frequency part of it is GM1, GM2, GM3, R1, R2, R3 times this guy. So that's basically your T0. And you can also find its, time constants associated with it, so it has a third order response. Now, if you actually do this and write those time constants, you can get what do you get? You will get, so basically you will get a T of S in terms of parameters that we defined. And if you take that T of S, and so which would look like this. So you can get basically T of S, which is T0, divided by the 3 time constants. Now, what are the new time constants? Are they the same? Well, they are kind of the same. This time constant and this time constant are the same. So you can write it as tau 2 or tau, did you call them tau 1 and tau 2? Yeah, tau 1s and 1 plus tau 2s. They haven't changed. This input time constant has changed a little bit, right? Because it was Rs in parallel with Cin, because now there's a second resistance because of the feedback resistance. What is that second resistance that's in parallel with Rs? RF plus Rm, right? Because it's RF plus Rm. Exactly. So there's a 1 plus tau in prime S, and tau in prime is Rs parallel Rf plus Rm4 times Cn. Fine. And you can calculate these things. Now, what you really want to calculate is not, so these are loop gains, so I have to put the second line here. So what we are trying to calculate, I'm going to erase these values, open up some space. All right, what we really need to calculate is we are interested in roots of not T of S, but we are more interested in roots of this. Because these are the roots of the delta or the poles of the circuit. You're interested, if you want to determine the stability, what determines the stability of a circuit? The position of the poles. You want to see if you have right half-plane poles or not. And we are trying to find ways to determine where these poles are. So now if I plug in numbers and calculate this quantity, so 1 plus T of S, I mean, you can write it in terms of the parameters that we wrote, right? It's going to be tau in prime, tau 1, tau 2, S cubed plus tau in tau 1 plus tau in tau 2 plus tau 1 tau 2 S squared plus tau in prime, they're all prime, tau in prime plus tau 1 plus tau 2 S plus 1 plus T of 0 equals 0. So you get something like that. And you can plug in numbers, right? I mean, now we have a numerical thing. So if you plug in numbers, you will get you get a transfer function that looks like this. I mean, so I'm going to put some numbers just for you to see how these things will look like. So it becomes 9.313 nanoseconds cubed, S cubed, plus 13 nanoseconds squared, S squared, plus 6.49 nanoseconds S plus 9.810. So there are S squared, S cubed, and these are some parameters. So this is basically what you get. So now, what do we do with this? You can plug it into mathematical MATLAB and say, okay, well, find the roots, and that's one way. Yeah. Works nowadays, and that's fine. There's nothing wrong with that. But how do we know where the roots are? The mere fact that these coefficients are positive doesn't mean that the roots are they're all negative roots, right? We know this. And there are methods that people have developed to look at this. So there are methods that numerical, like Ruth-Hurwitz method, that we'll talk about briefly next time, to determine where this is. There are also graphical methods where you can actually plot this, and by looking at the plot, you can see where it is, like Nyquist method. And this is for linear, and then for nonlinear stuff, there's also methods that have been developed, which are quite remarkable, that actually you can have general methods for nonlinear stuff too. But that's a pathway we'll take. So in this case, if you actually find the roots, you can actually find where things are for different values of t0, etc., and then you can find where the poles are. So you will see that you have, in this example, for the values that we had, you have two right half plane poles, which is what produced those like sinusoidal response. Now, we will make one change to the circuit. And that's actually the part that makes it quite interesting. So the change we are making is that I'm assuming that these capacitors have some resistance in series with them. And this is not an unreasonable assumption at all. Because, for example, there can be series resistance for the gate, there can be channel resistance, things of that. So your gate can have resistances. So there's a resistance. Let's call it R1. We have used R1. What did we call them? Okay, RZ1 and C1 and C2 RZ2. Now, you can probably guess why we call them RZ1 and RZ2, right? Because now, you remember when we talk about creation of zeros? One of the ways to create zero was to create this parallel RC path. And the reason it produces zero is that now if you short circuit this, there's still some signal going through because you're not truly short circuiting it. There's a resistor left here. So now you can easily see that there are two zeros. They're uncoupled zeros. They're two zeros, and they're what? Left half plane or right half plane? Do they change the polarity of the signal flow? No. So they're left half plane. The two left half plane zeros now in the new transfer function. So the new transfer function is going to be the same as old one, or it's going to be the open loop transfer function. It's going to be a tau z1s and 1 plus tau z2s. And you can easily calculate these two. Basically, these tau z1s are this RC. So tau z1 is really R1, RZ1 C1, and tau z2 is RZ2 C2. We've done these kind of things before, so it's pretty straightforward. Now, these also modify these time constants for the poles. So these will change. How would they change? Think about it. The time constant for C1 now, instead of being just C1 times the resistance seen by C1, what was it before when this guy was not there? It was just R1, right? So what is it now? R1 plus RZ1, right? So these time constants also change. So these become R1 plus RZ1, and this becomes plus RZ2. But other than that, the general behavior remains the same. So this is the same thing times C1. Now this new thing times C1 and C2. So these are the new time constants. Well, maybe I should put them as primes with this color to match that. So these are like tau 1. Tau n doesn't change because that resistance hasn't changed. It hasn't changed, but it's basically this new tau that we calculated somewhere. I don't know where I put it. So this input time constant is also Rs and Rm. So this resistance really is Rs plus parallel Rf plus Rm4, right? Because this now resistance also produces a little bit more extra capacitance. So that's the tau n prime. Okay, so this is tau n prime in general, if RF is there. Okay, so now what do we have? So let's look at this and see what happens. So you can calculate these things, and you can write a transfer function, and this is the way this transfer function will look like. Now, what the key question is that you're going to get, now for this new transfer function, you're going to be interested in 1 plus the loop gain prime, with this new loop gain, being 0. And you can write this in another kind of like numerical format, right? And if you write this in another numerical format, so it gets 6.32, some numbers, right? I'm not going to waste too much time on this. S cubed, so it's some numbers, right? So you have 2.368 nanoseconds squared S squared plus 606 nanosecond S plus 401 equals 0. Again, all the positive coefficients are positive, but we can't tell but just by looking at it. So we have to apply something like Ruth-Hurwitz, or you have to factor this somehow. And again, we'll see more systematic ways of dealing with this in the next lecture. But the key question, the key interesting thing about this thing is that, what I think the most important probably takeaway from this is that if you look at this, now let's look at this loop gain, right, that we evaluated. So this is the Bode plot of that loop gain. So you see that there are 2 points. And you see also on the phase plot, you see the phase wrapping. So when it goes to negative 180, it comes back to positive 180. So there's nothing extraordinary happening. But just you can see that at those 2 points where it's flipping, what has happened is that you have a forward gain, a loop gain, magnitude greater than 1, because you're above 0 dB in both cases. Right? So you have a loop where you have a return that's going to be larger. When you break the loop, what comes back is going to be greater than what went in. And if you want to see this more explicitly, so you can see that at these 2 frequencies, we actually opened the loop and applied that signal. This is very important, actually. So look at these 2. The output is larger than the input, and it's completely in phase with it in both of these cases, because you have 180 for the loop gain, and there's a minus sign in the loop gain definition, so it's like 360. So the signal's going in, it's coming back exactly in phase, and it's larger than what went in. Vy is greater than Vx, and it's exactly in phase. So intuitively, you may think that, okay, what goes in comes back stronger, so next time it goes back in, comes back stronger, so it's going to grow, right? And there are 2 frequencies at which it grows. But now here's the punchline. This is the step response of the system. It's a decaying sinusoidal. It is stable. This system, despite the fact that there are 2 frequencies at which you can put something in that would come back exactly in phase, 2 sinusoidals, that you put a sinusoidal in, comes back exactly in phase and larger. There are 2 frequencies at which this happens, but this system is stable. I mean, more precisely, this is called conditionally stable, but stable. Meaning that we have a bounded input and bounded output. And this should be counterintuitive. And if it is, it's good because it makes you realize that the intuition may not perfectly work, or at least simplified intuition may not work. And we need to develop more advanced tools. And that's what we'll do next time to understand this.